Okay, so good afternoon, everyone. So in this talk, I try to speak in English because I want to target a wider audience. But in case you have some question, feel free to ask it in either English or Cantonese. So thanks for having me today. So I'm happy and glad to be here and share my experience. So as a brief intro, I'm Alex Lau, so currently based in Singapore. So I'm working as a AI software engineer in Pencil. So today I would like to walk you through one of my side projects that I did in July. It's essentially my experience trying to implement a DietNeRF. Essentially, it's a model in Flax and JAX Community Week. It's essentially an open source initiative program, which I will introduce later. So I would start off with the motivation why I would like to start off the project and also introduce the tech stack that I use. And then I will briefly introduce the background of the project. It's good to grab some context on the project, essentially the model in principally, how do they work? But also I want to talk about the difficulties that we encounter throughout the project. And I think I want to cover this because it feels like the whole project sounds more realistic. I believe whenever we start our project, in the mid, we must encounter some difficulties. And I think it's good to disclose them. And I believe everyone may have some takeaways from that. Finally, I will have some demo of our project. Lastly, I will try to summarize some takeaways throughout this project. So actually, how did the project start? The project started off with an open source initiative organized by Hugging Face, which is a pretty popular NLP organization, open sourcing an NLP framework. Transformer is one of their invention, and also co-organized by Google Teams. So the whole initiative is called Flax and JAX Community Week. So essentially, it's a sprint lasting for a few weeks. Its goal is to make these kind of deep learning project, which is pretty computationally intensive, accessible to a wider audience. So essentially what they do is that they will offer a free access to TPU, which is from Google Cloud Platform for a week from July 7th to 14th. And then I think throughout the program, they also want to promote the framework they have invented, namely the transformer and the dataset library, which Hugging Face lately invented. And also the JAX and Flax framework, which is developed by Google Research. So they offer a lot of talks and tutorial on how to use them. And since the sprint is only lasts for a few weeks, it's pretty short. So they also offer some sample training script for us so that we can narrow down the scope, can complete our project easier, shorter time. So by the time I skimmed through the program, everyone is free to throw out their project ideas in the Hugging Face forum. So by the time I skimmed through one post, which is posted by Stella, which is one of our team member. She is a PhD student. Essentially, she wants to implement a paper which is called Putting NeRF on a Diet. Essentially, it proposed a model called NeRF, which stands for Neural Radiance Field. So by the time I want to learn more about NeRF, I didn't know much about NeRF by the time, but I see a lot of amazing experimental results coming out from NeRF. So I would love to learn more about that, and also its associated computer graphics techniques. So that's why I decided to join the team. And also by that time, I didn't know much about JAX, and I haven't tried TPU before. So I think it's a good chance for me to learn more about this new technology. So that's how we start. So at the end, the post received a lot of response. We have a number of teammates. So here, let me take this chance to introduce some of our core members. We have Stella and Shiyong from Korea. They are both PhD students specialized in computer vision. And we also have Kali from Bangladesh. We also have Haswan from India. So about the tech stack, right? The JAX and Flax are the major deep learning framework that we use throughout our project. So I would like to briefly introduce them because it's something I believe is pretty new to the audience. JAX is designed for high performance computing. It is developed by Google Research. Its interface is pretty much like NumPy, and in addition to that, it supports three main features. The first one is the auto differentiation, which using the JAX framework, you can transform a Python function into its derivative. You can get something like an output. The output will be its derivative. And secondly, it has a factorization. It can easily replace a for loop by its JAX syntax, which is VMAP and PMAP, which do the parallel computing or distributed computing across different TPU cores. Lastly, it also has a just-in-time compilation. What it does is that it tries to unroll the Python function into something like a static graph and then compile it in the optimal way so that when the second time onwards you run it, it can run pretty fast. So a lot of people will ask the question, what is the difference between JAX versus other popular framework like TensorFlow and PyTorch? So I can summarize a few points. First difference is that JAX can be easily run on CPU, GPU, TPU, all kinds of devices without any code change. It's pretty convenient. Another is that I feel like JAX is more generic in the sense that not only it can be applied in deep learning, it can be applied in any other machine learning library or some other pre-processing step as well. Let's say you have an image processing helper function which make use of NumPy. You can easily replace that by JAX, and then you can enjoy the benefit of running it in GPU or TPU. And numerically and empirically, I found from some study that JAX generally run faster compared against other frameworks when you are running in some kind of control settings. And for the Flax, it's essentially just a deep learning framework that is built on top of JAX. So for more information, I highly recommend this YouTube talk to get an intro on TPU, JAX, Flax, and transformers. Also highly recommend to read the JAX documentation for more information. So as for the demo, we mainly use two framework, which is Streamlit, essentially just an easy to use Python framework built for data scientists. It's designed for data scientists to build a web app for machine learning application or data science application super fast. And lastly, we have Spaces, which is a latest platform released by Hugging Face. It's designed to help engineer data scientists to host their machine learning app publicly very fast and easily. So I'll talk more about that in the demo. So next, I would like to talk more about the background of our project. So what is DietNeRF? The model that we try to implement essentially is a variant of NeRF, which stands for Neural Radiance Field. The advantage of this model is that it can efficiently train on very limited samples, something like 4 samples, 8 samples, 14 samples. So this is the distribution in a nutshell. So you naturally have some question. What is NeRF? What kind of issue does it have? And how could DietNeRF help? So I will address them one by one. So firstly, what is NeRF? NeRF is the latest deep learning model as far as I can recall, released last year or 2019, as I recall. Essentially just a neural network, which is pretty lightweight, just a stack of dense layers that try to learn to represent a 3D scene from its 2D snapshot that is taken from different angles, or I would say poses. So you can imagine a 3D scene as a volume. So what the neural network is trying to learn is that it's trying to learn to query any point in the volume, and the neural network is able to tell you the properties of this point. So the model requires 2 inputs, which is namely the coordinate point in the scene that you want to query, and also the field interaction. The field interaction is important because it will determine the properties of the point differently. So the model output will be the properties of the point. Essentially, it's the RGB color of this point and also the density of this point. So the field interaction will impact the RGB color, because if you feel the same position but with different angle, you will have different color. For example, the light illumination will be different. But the model can represent can volumetrically represent a 3D scene, but there's a problem. We cannot see the 3D volume because it's high dimensional. So we apply some technique to render a snapshot from this 3D scene. The technique we use is called classical for volume rendering. Essentially what it does is that it tries to project a 3D scene. I mean the samples that we query from the 3D scene, project them into a 2D plane and render pixels into this 2D plane so that we can have a 2D snapshot of the scene. So I will briefly walk you through how this volume rendering technique work. So I would like you to focus on the diagram on the right-hand side, the upper one. So just ignore the ray 2 and its associated 2D plane. Focus on the ray 1 and its associated plane. So firstly, what we do is we just focus on one pixel. We will firstly mask through a light ray from our eye, pass through the pixel, and then pass through the 3D scene. Next, once we have this light ray passing through the 3D scene, we consider the segment that pass through that, and then we try to draw samples along the light ray. So once we have this sample, we can feed those samples into a model because we have a fluid direction, which is coming from the light ray. And also we have the spatial position of each point. So what we can do is we can feed those quantities into the model. The model will evaluate the properties of each point. So what we get is the density and the RGB color for each sample. So if you look at the lower diagram, it visualizes the color which is represented by the color of the curve and also the density of each sample, which is represented by the y-axis. So once we have all these quantity for each samples, we can apply some volume rendering formula. It is essentially an integration. We will apply some numerical integration across all those samples and those quantities so that we can collapse the quantities of those samples into one single RGB pixel color. So we will repeat all these steps for all the pixels, and then we will end up having a nice 2D snapshot of the 3D scene. So as for the NeRF, it requires some training data. The training data it used is this 2D snapshot that is taken from different poses of the same 3D scene. To train the model, you also have to associate the 2D snapshot with its viewing pose. I mean, which angle and which position you are taking the image. Also, the neural network should have some objective for optimization. So the objective is to minimize the difference between the render colors that the model gives and the ground truth color from the ground truth 2D snapshot. And then since it's too expensive to evaluate all those pixels, we will only consider a sample of pixel. And then in this case, we use technical term is mean square error to close the difference. And then once you have a trained NeRF, you can have a volumetric representation of the 3D scene. Then you can 3D render any snapshot that you want from any angle and any pose. So here is one very nice example that is demonstrated in the NeRF project page. Essentially, it's trying to learn a 3D flower plot, and then you can draw a continuous motion to view this 3D flower plot, and then you end up have this very nice, smooth, and realistic 2D snapshot continuously, so that we can render as a video. So NeRF is pretty good, but it has a lot of problems. So one of them is that a typical NeRF requires a lot of diverse samples to train. For example, a few hundred. So as a result, it's pretty impractical to be deployed in real life because it's very expensive to take different snapshots of the same scene over and over again. To illustrate this point, we try to do an experiment. Essentially, we're trying to train a 3D ship scene, as you can see on the right-hand side. We only use 14 samples, which is pretty sparse. And also it is biased against one side only. As you see, this training sample only see one side of the ship. If we train this on original NeRF, what we can see is that it failed to render a 2D snapshot from another side of the ship. You can see that it's pretty blurry, and you can see some artifact in the background. So that's the drawback for NeRF. It will struggle on novel field when it is trained on limited and biased samples. And in the DietNeRF paper, the author tried to hypothesize the reason. They think that the reason is that the vanilla NeRF lacks some kind of prior knowledge, aka some kind of visual prior concept. For example, when you look at one side of the ship, you should easily infer another side of the ship. They should probably look similar, but NeRF lack some knowledge on that. So how could DietNeRF help? The solution is that during the training, we try to introduce a pre-trained model which encapsulates enough of visual prior knowledge, and then we use this kind of pre-trained model to regularize the original NeRF. So such kind of pre-trained model, the paper introduced is called CLIP. Essentially, is a latest vision and language model introduced by OpenAI that can jointly encode image and text together. So you can see that in the past you have a sentence vector which can embed the sentence into a embedding space. Right now, Clip move one step further, is trying to encode or embed image and text in the same space so that you can understand them all together. So the paper introduced the semantic consistency loss, which is using the Clip. So the principle is straightforward, intuitive. The idea is that if the snapshot are taken from the same scene, even though they're taken from different angle, different poses, they should share similar visual concept. And such kind of visual concept should be captured by Clip. So what we can do is that we can encode the ground truth 2D snapshot and also the render 2D snapshot, which is rendered by the model using Clip. And then we can enforce these two factors to be similar over the training. The way to do this is trying to make them to share a high degree of visual concept. So the way we capture the similarity in this case is using a term called cosine similarity. So essentially, the semantic consistency loss is essentially comparing the cosine similarity between a encoded render snapshot and the ground truth render snapshot. So with this in mind, our plan at the beginning of our project is straightforward. We want to start off with some existing NeRF implementation. We don't want to reinvent the wheel. We don't want to start from scratch. We start off with a base code, and then we want to introduce a clip model into the code base, which we can easily find in Transformer. And then we want to implement the semantic consistency loss in the training loop. It sounds straightforward, but it turns out we got stuck very soon. So in the following, I would like to introduce some difficulty we encounter and how we address them. The first difficulty we encounter is that the training speed in TPU Google Cloud platform is very slow. We are trying to build our code base upon an open source repository. It looks straightforward, pretty simple to make change, so we decided on that. But later on, we found that this implementation is not well optimized in TPU training. It ends up we need to rewrite a lot in order to make it to run fast in TPU. Remember, our program only lasts for a few weeks, and the TPU only open for 1 week. So we definitely want to make the training iteration fast. But what we found is that we don't have much knowledge on JAX. So we have by that time, we have two options. Either we keep improving the existing code, or we can find out a better repository that is well optimized on TPU. But by that time, we decided to take the former decision, and we end up spending a lot of time rewriting the base code, but didn't get a lot of significant gain in the speed. So on the right-hand side, you can see some of the example speed that we get. With a lot of improvement, we can end up to have something like taking 1.5 seconds to complete one iteration. We usually have a lot of iteration. It takes 150,000 iterations. So we end up, we need to take more than 60 hours. It is far from desirable. So ends up, we need to make a hard decision in the later stage to make a migration from the original code base to another implementation that is originally optimized in speed and TPU. So the code base that we try to migrate is called JAX-NeRF. Essentially, is you can find it in the Google Research repository. It is well optimized in TPU, and you can train the NeRF with this repository very fast in TPU. So by the time we used to hesitate the migration because we thought that the code base is pretty complex. With our limited knowledge in JAX, we may have difficulty making a change. But by the time I try to run it in TPU, I think the speed is super fast. It takes only 13 milliseconds to complete one iteration for the original NeRF, compared with 1.5 seconds. So in this case, the speed gain that we get is definitely outweigh the complexity of the model of the code base. So at the end, we decide to migrate a code base and do the semantic consistency loss integration there. But later on, we also find that another issue is that it's super expensive to evaluate this semantic consistency loss, because you have to render the whole image and you have to render every single pixel in the full image. So at the end, it runs out of memory very quickly, especially for high resolution. So by that time, unluckily, the TPU access has been closed. We have spent so much time on our first repository, and it didn't work. And ends up we have to move our development platform in the Google Colab Pro. By the time I start register a Google Colab Pro by the time and start doing the experiment there, we try a number of workarounds in order to get rid of the out of memory. Since our Colab Pro do not have only have 16 gigabyte memory, by the time we try to use a mixed precision to change the float 32 data type into a float 16 data type to reduce the memory. We also try to downsample the render view to render less number of pixels in order to reduce the memory consumed. We also try some tricks, something like to only render a random crop of the view and have a higher resolution to see that whether it can improve the result. After a number of experiments, we finally make it. On the left-hand side is a chat record to witness the breakthrough. By the time we have made a lot of attempts, TPU close, we can only run it in Colab. We run into a lot of issue on memory, running out of memory because we have limited resources in Colab. Throughout a number of iterations, we finally get some interesting result, as you can see. Using only 8 limited training sample, we can have a pretty nice rendered Lego snapshot. So with this implementation, we go ahead and do more experiment. On the right-hand side, you can see we are trying to compare the DietNeRF with NeRF. And it is also trained on 14 samples only, which is biased against one side. As you can see on the left-hand side, the DietNeRF can manage to render a novel views, the unobserved region pretty nicely. Although you can see some blurry side, but I think it's relatively clear compared against the original NeRF, which is pretty blurry on the unobserved region. So after this, we also make a demo, which is hosted in Hugging Face Spaces. Let me introduce it. So for time being, I've navigated to the demo. So on the right-hand side, you can see the render image that is rendered by our DietNeRF. In this case, we only trained it on 8 training samples. And on the left-hand side, you can see three panels, which allows you to control which angle you would like to view this 3D scene. In this case, it's a microphone. Let's say for the rotation, I can adjust whether I change my viewing from anti-clockwise or clockwise. In this case, let's try to view it anti-clockwise a little bit. Luckily, this demo is powered by a GPU device. So originally it runs super slow. It takes somewhere like 1 minute to render one image if we use CPU. But right now, you can see that it can render an image in less than 20 seconds, which is pretty nice. So more mention about this Spaces platform. Essentially, is a platform that you can set up your repository here. And then what you need to do is you need to specify the requirements, the package that you need to install. You need to specify the app.py, essentially the demo that you want to run. Specify it here and push your code. Once it's done, it will do the automatic deployment, deploy the whole thing into the Hugging Face Spaces platform. And you will see some nice demo here. From my experience, so you can feel free to go to our platform to play around with it. Also, attached to GitHub repository and the project report. So feel free to look around on it. So from my experience on the Hugging Face spaces is pretty good. I think it's pretty easy to use and make the whole deployment easy. Thing that I like is that it supports the version control, although it doesn't have branching, but it can track the history, the changes that I've made in the repository. And also it supported automatic deployment, which makes things pretty easy. But at the end, even though we have wrapped up a project, there's still some unsettled myth that we haven't been addressed. One myth is that we cannot nicely reproduce the result that is stated from the paper. So in the paper, when they have different training setting, in one case, they try to train on 14 samples, which is biased, also train on 8 samples. When they try to do the comparison against the original NeRF, as you can see there's a sharp difference. If it is trained on the original NeRF, when you render an unobserved region, it is completely blurry, it's completely invisible what this scene is about. But what we found is that actually the original NeRF, when we train on the same data set, is not as bad as the paper state. This is the on the bottom, the GIF is the result that we get when we train on our own. We found that, having said that, the unobserved region is blurry, but is still visible and pretty nice. So we cannot really reproduce the bad result in the original NeRF. And also when we try to train on the examples only, the quantitative and the qualitative result that we get is only slightly better for the DietNeRF compared against the original NeRF. So at this point, we still don't have much idea on what goes wrong, probably because of it may have something to do with our difference in the implementation on the semantic consistency loss. In some cases, if we have to downsample it too much, or we try to do some random cropping, it may impact the reliability of this loss term. It may also have something to do with the difference in our implementation because we use JAX implementation, but I believe the original paper is using a PyTorch implementation, or it's simply because of randomness. Maybe because of the different initialization in the weight, the slightly different training samples, etc., etc. So at this moment, we don't have any idea yet. So finally, some lesson that I can draw from this project. So firstly, it's really important, I think, to pick a good base repository that you can build on. From our experience, we have spent a lot of time optimizing our code, but end up didn't get a significant gain. It's definitely way better to have a list of repository that you can pick at the beginning and try to run it on TPU. If I can go back, if I can do a time travel and do that again, I would definitely try to dry test it in the TPU without any change and see which one have a faster speed. And from this, we can make a decision which repository we should we should pick. And finally, try to collaborate. I think it's really good to collaborate. Throughout this project, I have a really nice collaboration experience. And it's good to collaborate because you can meet a lot of friends. You can learn a lot from your teammates. From the project, and also can complement your weaknesses as well. Also, third point, try to publish your work. I think it's a very good way to make a connection. Stella, one of our teammates, tried to publish our work in the Twitter. End up, she managed to reach out to the first author of the paper. So I think it's a good way to connect. Also, I think it's a good way to attract more like-minded teammates to work on our project. Because our project will have a second stage, we are planning the second stage of our project. By that time we publish our work, we receive a lot of response from researchers who are working on the related field, PhD student working on the related area who show interest to joining our team. So I think it's a good way to expand our team and work with more like-minded people and great people like them. Also, it's a good way to get sponsorship. By that time, luckily we get sponsorship from a company which kindly help us to offer us a multi-GPU server so that we can train in addition to using a Google Colab. Finally, it's a good to showcase your portfolio. So definitely it's worthwhile to publish your work. Fourth point, I think we all know that deep learning is a pretty computationally intensive work. We may tend to buy some very expensive hardware resources to support them, to get a better experience or get this to work. But firstly, don't estimate the free resources. I think it's always good to start off with some free resource such as Google Colab or Kaggle kernel first to see whether it will work, whether the resource is enough to work in the free resources. From my experience, having said that, our model is really very memory extensive. We can make some workaround so that it can be experiment on the free resources. So 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 yeah. Finally, just get started and learn along the way. By that time, I don't know much about JAX or NeRF or related computer graphics technique, but throughout the way, I learned a lot about all of these aspects. I won't say I understand all of the content which is covered in the project, but at least I will think that is a really good entry point for me to learn something new. It gives me a context on why something is useful, why it is important for me to learn, and also is a way to give you some context on why you should learn something new. And it's never too late to learn it along the way. I believe there are a lot of resources for you to easily pick up the technology. So yeah, so lastly, if you want to check out more about our work, we wrote a blog post which is shown on the right-hand side in Notion. You can check out a link to read more about the nifty-gritty detail about DietNeRF. For time being, I can't introduce too much details about this model. Actually, in the original NeRF, there are a lot of details, how they do the get around on the model architecture or how to speed up the training, something like that. You can check out the blog post for more details like this. In addition, you can also check out our Streamlit demo, which is hosted in the Hugging Face Spaces in the second link. And if you want to check out our source code, you can check out our GitHub repository as well. Finally, we also archive our project into papers with code. You can check it out. So finally, I think that's pretty much my talk. Finally, some resources I would like to share. If you want to learn more about JAX, I highly recommend the first four resources. The first one is the YouTube talk that I attached in the previous slide, and also the JAX documentation. Also, I highly recommend the fourth link. It is essentially a Kaggle kernel notebook, which is prepared by a senior data scientist, Akash, trying to introduce the JAX throughout the way with some hands-on code. I think that the whole tutorial series is really valuable for you if you want to dive deep to understand the JAX framework. Finally, some paper references related to NeRF. And also lastly, the paper related to Click. I believe is a really powerful technology that we can use in many places. So highly recommended to check it out. So I think that's pretty much it. So thank you. So lastly, thank you for having me again. And if you have any question, feel free to ask it in either Cantonese or English. So I'm glad to answer.
Thank you, Alex. Thank you very much for joining us to present. Okay.